Because we're going to look at circular motion and banked turns. So here we've got a NASCAR race, and why are the tracks banked at NASCAR? So the cars can go faster around the curves without skidding out, because the faster they go, the faster they crash, and the more fun we have getting to watch them run out of their car with their hair on fire. So we have to take a look at what's going on here when we have a banked turn. So if we look from behind the car, we have a very simple free body diagram if there's no friction involved. So let's say that this is a super icy road and this car is going around a banked curve. There's no coefficient of friction. There's no force of friction. All we have is the normal force on the car and the weight of the car. And this curve has some radius r. So if we were to draw it from above, the car is going around this curve like this, and it's got some effective radius r traveling around the curve with some velocity. And if that's the case, we must have a centripetal acceleration going in towards the center of the curve, a sub c, which also means that we've got a centripetal force going in the same direction, F sub c. So in this picture down here, drawing in our net force for the car, the F net goes straight in towards the center of the circle, not down the ramp, straight in the positive x direction, and that is equal to F sub c. And what we see here is what force or component of a force is supplying the force of centripetal force, sorry. That would be the x component of the normal force. So if we take a look at that component of the normal force, it's going straight in. The y component of the normal force is counteracting gravity. The car is not accelerating vertically, it is accelerating horizontally because it's going in a circle. So we actually have two possibilities to choose for our coordinate system. Now classically, when we've been dealing with the inclined plane, we have gone with this coordinate system right here, where we've got the positive x going parallel to the ramp, positive y is perpendicular to the ramp. And we can definitely do these problems that way. The other option is we keep our coordinate system classically, where x is straight horizontal and y is straight vertical. And we're going to take a look at solutions to this problem either way, and you can choose which one you like. I don't think the problems really are any easier or more difficult depending on the choice of the coordinate system. So let's take a look at solution 1. So here in solution 1, we have our coordinate system defined classically, where x and y are horizontal and vertical, and we've got our F sub c going straight in to the center of the circle. And we know that the horizontal component of the normal force is supplying that F sub c. We also need the vertical component of the normal force. So we call this ny, and this guy would be nx. And so we go to the sum of the forces acting in the x direction is equal to the centripetal force, and the sum of the forces acting in the y direction is equal to 0. Working on the x side here, we've got only the x component of the normal force acting in the x direction, and that's going to equal, let's break this down, ma sub c. So the normal force in the x direction, we have theta, our angle right here, so the normal force is going to be the side, sorry, the x component of the normal force is going to be the side opposite, so we've got n sine theta is equal to the mass times the centripetal acceleration in the x direction. In the y direction, we've got the normal force in the y direction pointing up. We have mg pointing down, and that's equal to 0. Breaking this down a little bit, we have the normal force times the cosine of theta here, because ny over here is the side adjacent to theta. So normal force times the cosine of theta is equal to mg. And let's see here. Probably the easiest way to see this is let's solve our y equation for the normal force. So the normal force is equal to mg divided by cos theta. And we're going to plug that in for the normal force over here. So we've got mg over cos theta times sine theta is equal to m times the centripetal acceleration. So we see that we've got an m on both sides of the equation, so the m's cancel. Bye-bye. And we have sine over cosine, so we can simplify that to tangent. So we end up with g tan theta is equal to the centripetal acceleration. That is a generalized result. Anytime we do not have friction involved in a banked turn, that's going to be the case. It might be worth remembering that. And we can break this down even further to put it in terms of the radius of the circle and the velocity, because remember that centripetal acceleration is v squared over r. So from this equation right here, we can solve for what you like. We can solve for the velocity, the maximum velocity. We can go around a curve of a given radius and a given bank. We can solve for theta, how much does it need to be banked so that the car wants to go around at 20 meters per second, a curve of radius 50 meters, etc. So basically we can solve for theta, v, or r for any given situation. And again, this is, all right, we're only going to attack this problem from one way. So we're going to take a look at our coordinate system to find the classic way with x and y, horizontal and vertical. Okay, so we're going to draw in our frictional force. So remember that if the car is going too fast to find the maximum, then our frictional force is going to be acting this way, down the ramp, parallel to the ramp, and that makes this angle right here also equal to theta. Okay, so in this case, we're going to have to find the components of our weight force, so mg in the y direction, and we've got, I messed that up completely. Let's go back. No, because our weight force is going straight in the y direction, we don't need those components. Sorry, we need the components of the normal force. So we've got the x component of the normal force, we'll call nx. We have the y component of the normal force, we'll call some crazy thing. How about ny? And unfortunately, we also, in this case, have to resolve our friction force into components. We've got the y component of the static friction. Let's just call it Fy, since we only have one frictional force. And we have the x component of the frictional force, Fy. So now notice that Fx, sorry. So notice that Fy down here is helping out the weight. So the normal force, Ny, has to counteract both Fy and mg. And when we look at Fx and Nx, those are the two things that are supplying our centripetal force. Okay, so let's go ahead and find values for all of these in terms of theta and Fs and N. So Fx is adjacent to theta, so we've got Fs cos theta. That makes Fy Fs sine theta. And then if we talk about our normal force, we look at Nx up here. According to that theta, he is opposite, so we're going to do Nx is going to be N sine theta, and Ny then is N cos theta. Now let's move to the next page and apply these. Okay, so here we are. We've got our components of friction and normal force, and we're going to go to the sum of the forces acting in the x direction is equal to the centripetal force, and the sum of the forces acting in the y direction is equal to 0. So over here on the x side, the forces, let's go back and take a look real quick. The forces acting in the x direction, we've got the normal force in the x direction, we've got the frictional force in the x direction. That's it. So Nx and Fx, and they're both going to the right or positive. So we have Nx plus Fx is equal to Fc. The sum of the forces in the y direction, going back and looking, we've got three forces and components of forces. The normal force in the y direction is positive, weight and Fy are negative. So we're going to have normal force minus mg minus Fy is equals 0. Okay, now we can break stuff down a little bit. We've got nx is n sine theta plus fx, which is f cosine theta. And centripetal force is mass times centripetal acceleration. Over here, this should have been normal force in the y direction. Sorry, that's going to be n in the y direction was cos theta minus mg minus Fy, which was f sine theta. That's equal to 0. So keep in mind here, we're going to basically solve for a sub c. And let's get rid of the normal force. So over here on the y side, let's solve for the normal force. We have n cos theta is equal to mg plus f sine theta. Oh, before we even do that, hold on. We have to resolve our frictional forces because those are coefficients times normal forces. So let's do that on both sides. We've got the normal force times the sine of theta plus mu times the normal force times the cosine of theta is equal to m a sub c. On the right side, we have n cos theta is equal to mg plus mu n sine theta. So probably the easiest thing is to solve both for the normal force and set them equal to each other. So let's factor out an n on the left side here. We've got n times sine theta plus mu cos theta is equal to m a sub c. Solving for n, we get m a sub c over sine theta plus mu cos theta. Over here, sorry, we're going to have to move this guy back over to the right-hand side and factor out an n. We've got normal force times cos theta minus mu sine theta is equal to mg. And dividing out, we've got the normal force is equal to mg over cos theta minus mu sine theta. So we have these two now equal to the normal force. We can set them equal to each other. And we can now solve for a sub c. So if we multiply both sides by this guy right here, we get m a sub c is equal to mg times sine theta plus mu cos theta, all divided by cos theta minus mu sine theta. And we have an m on both sides, which we get to cancel out, which is interesting. The mass of the car doesn't matter. So we have a sub c is equal to all that ugly stuff on the right. And substituting in v squared over r for a sub c. V squared over r is equal to all that ugly stuff. So here then is our starting point for solving for things like what is the maximum velocity a car can go through a curve of radius r and bank angle theta if the coefficient of static friction is some coefficient mu. So you just multiply both sides by r, take the square root, and that's going to give you v. This result is not nearly as easy to memorize. It's not easy to derive either, but there it is. So for your assignment, right now, I would like you to work on the following. All right, so at your table groups, go ahead and work on Chapter 5 problems, 94 and 95. And it's really pretty much an easy exercise to apply the equation that I just came up with, but it's worthwhile for you to go through the algebra yourselves to get a handle on how to do this. And actually, for problem number 95, you aren't going to be able to use the equation that I gave you because they're asking you for different things like the normal force and actually the force of static friction. So good luck. Get these done. You won't have any homework over break. Enjoy break. I'll see you guys when we get back.